Okay, hi, my name's Angus Chadwick, and today I'm going to try to convince you that rotational dynamics are actually optimal for noise-robust working memory, and that they can reconcile some apparently conflicting experimental observations. So working memory is the ability to hold information in mind after removal of sensory input, and then after a delay, report it behaviorally. So there's been a substantial body of both experimental and theoretical work trying to understand the neural mechanisms by which working memories are stored in the delay between sensory input and motor output. So classic work going back to the 1970s has argued that memories or working memories are stored during stable and persistent patterns of neural activity during the delay. But more recent work, driven by advances in experimental recording technologies, has instead shown that working memories may be stored in highly dynamic and time-varying patterns of neural activity which are constantly changing throughout the delay. So there have been a number of computational models put forward to account for various aspects of persistent activity and dynamic coding. So low-dimensional attractor dynamics could be used to load the stimulus into a persistent attractor state where it stays throughout the delay. Or more recently, non-normal models have been proposed where stimuli are loaded into a transiently amplifying activity pattern before they settle into a persistent state. In higher dimensional models, you could have multiple stimulus-tuned attractors. You could have chaotic dynamics, which generate long transients throughout the delay. Or you could have functionally feed-forward dynamics that generate sequences of neural activity that span the delay. And so each of these models can account for certain aspects of either persistent coding or dynamic coding, but reconciling all of the available data within any one model has been challenging. So to address this, we asked whether persistent and dynamic coding might both emerge from the optimal noise-robust dynamics for working memory. So we developed a method to optimize continuous time linear RNNs driven by noise to maximize their working memory performance. And this method doesn't require backpropagation through time. So in this toy example, there's just two neurons and one of two possible stimuli. The stimulus has a brief pulse of input and ongoing noise, which corrupts the stimulus representation over time. It's fed into this two-neuron recurrent network, and then after a delay, there's a linear readout applied. And we optimized both the recurrent connectivity and the readout weights to maximize decoding performance at the end of the delay. And so surprisingly, what we found were that the optimal dynamics didn't correspond to any of the previously proposed solutions, but that instead rotational dynamics carried the stimulus throughout the delay. So these rotational dynamics were even more striking when we optimized higher dimensional networks. So there we found a functionally feed-forward sequence of rotational planes. So in this case, generating these high-dimensional rotational dynamics in this six-dimensional space. And this generated highly time-varying and dynamic patterns of single neuron firing rates, as seen in dynamic coding experiments. So to compare this more directly against experimental data, we extended the framework to handle the case in which one of many stimuli has to be represented throughout the delay. So here we show a minimal model with just 4 neurons. Each neuron receives input which is tuned to one of these 8 stimuli. And on the right, you see the state space perspective of the input. So we have this 4-dimensional input space, and the inputs are restricted to a circle, which is embedded in a 2D subspace of this 4D input space. And what we find then is that the optimal network exhibits 2 independent and orthogonal rotational planes, each of which integrates a different dimension of this 2-dimensional input space, rotates these inputs throughout the delay, and then the linear readout can combine information from both rotational planes to decode which of the 8 stimuli was presented. So finally, we asked whether this model could account for classic experimental data on both dynamic coding and persistent coding. So a hallmark of dynamic coding is this cross-temporal decoding analysis, where you train a decoder at one time in the delay and test its performance at another time in the delay. And the model produced the same cross-temporal decoding plot as the experimental data. Another feature of dynamic coding is switching selectivity, where single neurons will change their preferred stimulus from early in the delay to late in the delay. This was also replicated by the model. And a seemingly conflicting piece of experimental data associated with persistent coding is that the overall representational geometry of the population response is stable across the delay, and this was also replicated by the model. So taken together then, these results suggest that these high-dimensional rotational dynamics are optimal for noise-robust working memory and can reconcile persistent coding and dynamic coding theories of working memory. So thanks for your attention, and I hope to see you at the poster session later.